Today, I want to discuss with you how to work with stateless microservices, how to scale them, and what to do if your microservices is not stateless. In modern technology companies, a huge number of requests are processed daily, making the optimization of system performance and reliability critically important. Microservice architecture has established itself as one of the most effective approaches to developing scalable and resilient systems. However, to achieve the best results, it is important to properly utilize and implement microservices. Today, we will explore what stateless microservices are and why they play a key role in handling requests in high-load systems. We will discuss their advantages regarding scalability and reliability, key design principles, and implementation strategies. I will also share practical advice and examples to help you optimize your system's performance and ensure their resilience to high loads. Let's begin our exploration of these important aspects. In recent years, distributed systems and microservice architecture have become the standards for developing modern applications. These approaches enable companies to create flexible, scalable, and reliable solutions capable of handling high loads and rapid changes in requirements. Containers such as Docker and orchestration platforms like Kubernetes have become integral to the development and deployment of microservices. They provide isolation and scalability and simplify the management of application lifecycles. DevOps and continuous deployment approaches facilitate the automation of development, testing, and deployment processes. This enables faster delivery of new features and fixes, enhancing overall development efficiency. Cloud platforms such as Amazon Web Services, Google Cloud, and Microsoft Azure offer tools and services for developing, deploying, and managing microservices. This allows companies to quickly scale resources according to current needs. Observability and monitoring. A crucial element of managing distributed systems is ensuring observability and monitoring. Tools like Prometheus and Grafana help track the system state and respond promptly to emerging issues. I will leave security topics outside of the scope of this presentation as they require separate coverage. Obvious stateless microservices do not store any state between requests. In the context of each request, all necessary information is transmitted and processed without retaining any data or state within the microservice itself. This means that each request is handled independently of previous requests. Stateless microservices significantly simplify horizontal scaling. Since no state is retained, microservices instances can be easily added or removed to handle increasing or decreasing loads. In the event of a failure of one instance of a microservice, its request can be redirected to other instances without any loss of data or state. This enhances the overall fault tolerance of the system. Stateless microservices are easy to deploy and manage because they do not depend on stored state. They reduce complexity and the number of years during the deployment and updating of services. Since each microservice instance can handle any request, load balancing systems can effectively distribute requests among all available instances, improving the system's overall performance and response speed. Stateless microservices simplify the implementation of security measures such as authentication and authorization. Each request can be independently verified and processed, reducing the risk of data breaches and unauthorized access. Due to their independence from the state, stateless microservices simplify development and testing. This allows teams to develop, test, and deploy microservices more quickly and efficiently. I want to provide some examples of stateless microservices. First of all, API gateways are the central entry point for all client requests and distribute them to the appropriate microservices. They do not retain state between requests, which allows them to be flexible and scalable. For example, when a user requests profile data, the API gateway directs this request to the corresponding microservice, which processes the request and returns the data. Authorization and authentication servers. The servers verify users' credentials and create access tokens. They also do not store state between requests. Each authentication request is processed independently. For instance, all auth servers generate access tokens based on credentials provided with each request and do not retain user state between sessions. Load balancers distribute incoming requests among multiple instances of microservices. They do not store information about previous requests, but simply direct each new request to the least loaded or nearest server. This ensures even load distribution and prevents individual servers from becoming overloaded. Another example, notification services that send alerts to user can be stateless. Each request to send a notification is processed independently. For example, a service might accept requests to send SMS or email notification, process them, and send the appropriate message without needing to store information about previous notifications. Another good example, pre-trained model services. Services that host pre-trained machine learning models process requests to make prediction or classification without retaining state between requests. For example, a service using a pre-trained model for image recognition accepts an image as input, processes it, and returns the classification result. Each image is processed independently, allowing the service to easily scale as the number of requests increases. But what to do with stateful services? One of the possible decisions is hybrid services. Hybrid microservices represent an approach where the functionality of a service is divided into stateful and stateless components. This approach allows for efficient management of the state and scaling of services. Let's explore how this works. Stateless components handle incoming requests. They perform computations, data processing, validation, and other operations that do not require state retention between requests. These components are easily scalable because they do not depend on state. They can be deployed in large numbers, allowing them to handle a high volume of requests in parallel and evenly distribute the load. Stateful components are responsible for storing and managing state. They handle operations related to state changes and ensure long-term data storage. These components can use specialized data storage systems and ensure data consistency and integrity. You can hold all your microservice code base inside one repository and create different prompts or files to start stateless or stateful components. Moreover, you can have more than one unique instance of the stateful or stateless components depending on your needs. Again, the key trait of the stateless component is scalability. It should have an opportunity to be run in any number of instances without losing functionality and without possible race conditions. I will discuss race conditions later. Common Query Responsible Segregation, or cqrs, is a pattern that separates read and write operations, allowing for more efficient state management. In the context of microservice architecture, this pattern can be implemented as follows. You need to separate all requests to your microservices in two types. First is commons, write operations that modify the system state or data. These operations are handled by stateful components. And queries, read operations that retrieve data from the system. These operations are handled by stateless components. The cqrs pattern allows read and write operation to be scaled independently. This is especially useful in systems with high read or write loads. Data reads can be optimized for quick access and scaling, while write operations can focus on ensuring data integrity and consistency. The separation of operations allows for the use of different data models for reading and writing, which can simplify development and improve performance. Running a larger number of stateless components compared to stateful components is a key strategy for ensuring high system scalability and performance. Stateless components, which do not retain state between requests, are easily horizontally scalable, allowing for the handling of a large volume of incoming requests in parallel and distributing the load evenly. Meanwhile, stateful components, which manage state and data, usually require more complex management and synchronization, limiting their horizontal scalability. Let's talk about the interaction between stateless and stateful components. Synchronous interaction. I will call it sync interactions instead. It would be much easier for me to handle this word. How it works. The stateless component initiates a request. The stateful component processes the request and returns the result. The stateless component receives the response and completes the request processing. Simple. This type of interaction gives us several advantages. Sync interaction via HTTP or RPC is easy to implement and integrate into existing infrastructure. Clients receive an immediate response, useful for operations requiring real-time confirmations. It is easy to track data flow and interaction between components. But everything has a price. If the stateful component is unavailable, requests from the stateless component cannot be proceeded, leading to delays and failures. 500 errors. Sync calls can become a bottleneck under high loads, as each request requires immediate processing. Sync calls can increase latency, especially if the stateful component processes complex operations. Some practical recommendations. Use load balancers to distribute requests among multiple instances of stateful components. You can use remote procedure calls using a message broker like RabbitMQ. Unfortunately, it is not always possible to run multiple instances of stateful components, and it would limit your ability to scale your application. It would be useful to configure timeouts and retry mechanism to handle errors and temporary failures. Not every request can be retried. In case of retry, we do not know the status of the previous attempts processing. In such cases, it is necessary either to organize an idempotent request system, where a repeated request will not change the state of the state, or to abandon the idea of retries. Race condition, it's my favorite part, source of my daily headache. A race condition occurs when two or more components or processes compete for access to a shared resource, such as data or state, at the same time, leading to unpredictable or incorrect results. In other words, when multiple stateless components at the same time send requests to a single multiple stateful component, a situation can arise where they try to update the same state or data. If the stateful component does not properly manage access to the data, it can lead to incorrect updates and an inconsistent state. Several solutions to prevent race condition. First of all, locks. Implement locking mechanism in stateful components to control access to shared resources. For example, use database that supports transactions to ensure data integrity. Most SQL databases do it. Combine operations into transactions to ensure atomic execution, or all or nothing. You can try to achieve idempotency, ensure that all operations can be safely repeated without altering the result. Strategies include using unique identifiers, design inherently idempotent operations, employing transactional semantics, utilizing conditional requests, communication with appropriate response coders, and others. Idempotency is a big deal to fintech companies. They really like it because it helps them avoid spending money twice. You can also try data versioning, use record versioning, e.g. version fields, to check the currency of data before performing updates. Version checks before attempting an update. Each request verifies the data of version has not changed since it was read. If the version has changed, the request is registered and can be retried. Another effective solution is to move from sync interaction to async interaction. You don't need to wait stateful component, fire and forget. Some advice is how to implement it. You can use message queues. Our goal is to ensure reliable message delivery between stateless and stateful components and increase system resilience to failures. Queues like RabbitMQ or Kafka can be used to transmit commands. There is an old joke that no one has ever been fired for choosing RabbitMQ as a message broker. Okay, return to process. Messages placed in the queue are guaranteed to be delivered and processed by stateful components, and if temporary failure occur. How it works: an example of some online shop. Stateless component receives a request to create a new order and performs necessary checks and computation. It forms a command to create the order and place it in the message queue. The message is stored in the queue and awaits processing by the stateful component. Stateful component retrieves the message from the queue, processing it, and sets the new order data in the database. If necessary, the stateful component can send the confirmation back to the queue for subsequent processing, but better to avoid it. A huge percentage of our requests are successfully proceed, so if the situation allows, our stateless component can respond with a positive answer without awaiting the stateful component. It names an optimistic response. Another step is event-driven architecture. Separate operations and enhance system flexibility by allowing stateful components to respond to events generated by stateless components. How it works: stateless components generate events in response to specific actions or requests. Stateful components subscribe to events and process them, updating their state accordingly. It will work similar to the previous example, with the added benefit of additional handlers. Other components or even microservices, such as authentication systems or analytics, can also subscribe to this event and perform their actions. For example, sending an order confirmation to the client or updating seller statistic. It allows us to use optimistic responses by design with async interactions. A stateless component may not wait for an immediate response from a stateful component, but can promptly notify the client that the request has been accepted. The notification can include preliminary default data or simply a message confirming the request's successful processing. This approach ensures faster system response to requests, improves user experience, and more efficiently distributes the service load. Advantages of async interaction: message queues ensure a reliable delivery and processing of commands, enhancing system resilience. Async interaction facilitates easy scaling of individual components without the blockages and delays associated with sync calls. Event-driven architecture simplifies adding new functionalities and components, as new subscribers can be added without altering existing producing components. Some practical recommendations: it would be nice to implement monitoring and alert systems to track the status of queues and event processing, ensuring timely identification and resolution of issues. Pay particular attention to the number of unprocessed messages in the queue. If this number grows, something may be wrong. Also, it is important to establish clear contrast between components and document events and commands to ensure consistency and simplify the integration of new components. Okay, let's finalize. The discussed aspects demonstrate the importance of using stateless microservices and hybrid strategies to create scalable and reliable distributed systems. Stateless microservices significantly simplify horizontal scaling, as they do not retain the state between the requests. This means that instances of microservices can be easily added or removed depending on the current load, ensuring high performance and fault tolerance of the system, especially with orchestration like Kubernetes. Consequently, load balancing systems can effectively distribute requests among all available instances, improving overall performance and response speed. Hybrid microservices, in turn, enable efficient state management and scaling by dividing the services functionality into stateful and stateless components. Stateless components handle requests, perform computations, validate data, and carry out other operations that do not require state retention, making them easy to scale. Stateful components, on the other hand, manage data persistence and long-term state storage, which requires more complex management and synchronization, but ensures data integrity and consistency. Applying the cqrs pattern allows for the separation of print and write operations, enhancing the efficiency of state management. Data reads are performed by stateless components, while writes are handled by stateful components, allowing this operation to be scaled independently and optimizing system performance. Async interactions through message queues and event-driven architecture ensures reliable common delivery and enhance system resilience to failures. Message queues such as RabbitMQ or Kafka guarantee that commands are delivered and proceed by stateful components even if temporary failures occur. Event-driven architecture allows stateful components to react to events generated by stateless components, simplifying the additions of new functionality and components to the system. I greatly appreciate your attention and the time you taken to engage with me. Thank you for your consideration.